A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering, and I'll be dealing the subjects robotics in Institute of Aeronautical Engineering. And my today's topic is Joint Space Dynamic Control. In the previous sessions, we have discussed about the various concepts, generalized concepts, which we come across in the robotics subject. Now, the topics which we will be covering in this from this presentation will be the advanced topics which will be used in designing or constructing or for the movement or dynamics or motion of the robot manipulator. So firstly, coming to the joint implementations of the regulations in the robot, what do we mean by joint impedance? Yes, most of them are not aware what is a joint impedance and how does it work, or what are the various applications of this joint impedance in the robotics. So here, generally, this impedance refers to the strategy control, which is used to monitor the stiffness or the damping of the robot joint, right? That is when we have several links being attached to the robot, right? So here, in order to have a strategy control on this particular stiffness or on the particular damping of the robot joints, this joint impedance regulation is being used in robots. Right? So this is used to adapt the different tasks of the environment, whatever are the tasks being affiliated to the environment. Right? It is used to adopt the different tasks of the environment, and not only that, it is also used for the particular importance in situations where the robot is used to interact with the humans, or when the robot has to interact with the environment, or it needs to maintain a balance between the precision and compliances, right? There we use the joint impedance regulation, right? Firstly, the joint impedance is used in the robotics to have a control on the robotic joints, that is damping of the robotic joints or on the stiffness. And not only that, it is also used for the situations where the robot has to interact with the environment, or either it may be with the human, in order to have a balance between the precision and the compliances. Right? So this is about what the joint impedance is and why we are using it in the robot. Right? Now, next, let us see what are the main important concepts which come under this impedance, joint space dynamic control, or when we call it as the joint impedance. So here we need to have a control on the impedance. That is one of the key points, right? We need to have a control on the impedance, which is one of the very important point, or we should have a control on the stiffness or on the damping. That is, when we are considering any robot, it should involve the impedance control. That is the difference between the force and motion at the robot joints, right? For example, we have a robot here, right, which has been fixed at one, and this is the joint 1, this is the joint 2, and this is the joint 3. Now, with the help of the joint space dynamics, or with the help of the impedance control, we can have a control on these particular joints. Right? We can have control on these particular joints, that is with respect to the force or with respect to the motion of the robot joint, right? We should have a control with respect to the force or with respect to the motion on the robot joints, right? Or when we come across the stiffness, we should have a control on the joint resistant deformation, which can be applied with the help of the force, right? That is, the higher stiffness leads to less movement for the, as we all know, if for example, let us take a human body, right? We have n number of joints near the arms or the legs, or near the legs, right? So when the joint, whether it is a hand joint or whether it is a leg joint, when we have a pain or when the particular leg becomes stiff, can we move appropriately? Can we move fastly? No, right? That is it. It is getting tighter where we cannot have a faster movement. We cannot have a faster movement with respect to the leg or with respect to the hand. In the same way, the same happens to the robot also. When there is no proper stiffness condition, when there is no proper control in the stiffness, the robot will have less movement with respect to that but given force. So that is known as the impedance control. Right? When we come across damping, what do we mean by damping? It is with respect to the velocity, right? Where stiffness is applied with the help of the force, and impedance is applied with the help of the force and motion, and this is with respect to the velocity. That is, here control. We need to control how the system responds to the change in the velocity. That is helping the reduce oscillations and stabilizing the motion of the robot. When we need to reduce the oscillations or when we need to have a good motion, robot motion, with there is a change in the velocity, then we need to have a control on the damping also. Right? These are the three key concepts which we need to concentrate on when we are designing the manipulator of the robot. Right? Next, coming to the varial impedance. What do we mean by a varial impedance? Varial impedance means what? What comes across varial impedance? That is, as I've told you, the joint stiffness and damping. Right? When the robot has a varial impedance, we should adjust their joint stiffness and damping. When we are adjusting the stiffness of the robot's manipulator and we are adjusting the damping of the robots, that is known as the varial impedance. That is, here we require both force and precision also. Right? Here in the varial impedance, we require both force and precision, which is used for handling delicate objects or interacting with unprescribed environment. Right? This is generally a real-time example. That is in stiffness and damping in the real times. Right? Where we are acting on the force and precision, where the handling it is used for handling delicate objects or when we need to interact with the environment, right, with unpredictable environment, right. That is known as the variable impedance. Now, what are the applications? Where can we use these particular joint space dynamics, or where can we use this impedance, joint impedance? Generally, between when we need to have a human-robot interaction, or when we need to have a compliance motion, or when there is an we require adaptive control to be done. There all we require this impedance system. Right? Generally, for example, the human-robot interaction is nothing but cobots, right? Which is already been manufactured in India and it is already been used. So when we are coming across human-robot interaction, we should be very careful about the safety. Right? Because if a robot, whatever we are manufactured or constructed, harms or damages the other person in the environment, then that particular robot is waste. Right? So we need to concentrate on the impedance which helps in the safety and security when it is interacting with the human. Or when we come across compliant motion. What do we mean by compliant motion? Like generally, this requires soft touch. Like these particular type of the robots require the soft touch, like assembly or surgeries. Generally, in the hospitals, we use this particular type of compliance motion type of the robot, where we require a soft touch to be taking place, and it is generally used in surgeries or by modulating the joint impedance. That is known as the compliant motion. Next, coming to the adaptive control. What do we mean by adaptive control here? This particular adaptive control is one form of a application where it is implemented to deal with uncertainties such as change in object properties or unexpected obstacles. When we come across the unexpected obstacles, or when we come across the object properties, or when we come across dealing with the uncertainty environmental condition, there the robo has to adapt itself to control with respective perspective, right? This robo should adopt the environmental conditions and should work accordingly. These are the three main applications of the joint space dynamic control system. Right. Next, coming to the control strategies. How can the robo control itself? That is based on position, or based on the force, or based on the hybrid control. Here again we have three types of the control strategies. One is based on position. That is, we can adjust the position of the joints to achieve the desired characteristics, impedance characteristics. So based on the adjustment of the position of the joints of the robot's manipulator, we can get the desired impedance characteristics. Or based on the control on the force at the joints, we will be getting a regulate impedances on the particular robot, right? Or when we come across both position as well as position plus force. When we come across these particular two, position plus force, this is known as a hybrid control. Right? When we come across both, the combination of both position as well as the force control, then that particular type of the control strategy, that is it, this is one of the very versatile and adaptive robot behavior which generally we are using nowadays. Right? So that is known as the hybrid control system. Any robot which is acting according to the position of the where we are adjusting the position of the joints to attain the characteristics of the impedance, that is known as the position based impedance. When we are acting on adjusting the forces, that is known as the force based impedance. Now the combination of both position as well as the force is known as the hybrid control used in the robot. Right? And the challenges which come across this joint space dynamic are real-time performances, or whether it is when we come across the complex designing, or when we come across the trade-off. Right? In these are the three challenges which we need to focus on. That is, when we need to design any robot that can accurately and reliably mount the joint implements, right? Or when we require advanced sensors and algorithms, we need to concentrate on the complex design, right? That is, we have to take the challenge for designing a robot which is complicated, right? That is, whether it may be by usage of the advanced sensors, or by giving the high-end algorithm programming to the robot, or maybe it may depend upon the complex joint impedances. So we need to take any particular challenge and we need to start working on it. When we come across the minimum delay or real-time operations, or when we come across the effective, dynamic and unpredictable environment, then the real-time performance is also very important. Right? That is, when we are manufacturing or when we are constructing the robot, the real-time performance of that robot is very important. That it should have a minimum delay, it should be very effective, and it should have a very dynamic and unpredictable environmental constraint when it is acting in the real-time conditions. Right? Or when we come across the stability, or when we come across the flexibility, that is, stability means high stiffness or flexibility means lower stiffness. When any robot is high in its stiffness, then it is known as stable. Or it is low in stiffness, then it is known as flexible. Right? So any particular robot, when we are manufacturing, we should take a challenge that the robot's dynamic motion, that is, whether it is a kinematic or a dynamic motion being taking place, the joints may be stable or may be flexible. That depends upon the stiffness of the robots which we are manufacturing. We should carefully balance depending upon the task. We should carefully try to balance that depending upon the task given in that particular organization or in that particular industry. That is known as the trade-off. Let us take a practical example and explain how this particular joint space dynamic is exactly used. That is, here this is a physical therapy which is needed for the patients, right? This particular when a robot arm is used in physical therapy, which may need to assist a patient with gentle guided movement, or by regulating the joint impedance, the robot can adjust its stiffness. Right here, the robot is easily able to adjust the stiffness to match the need of the patients, providing the support without exerting excessive force that could cause discomfort or injury. Without causing any sort of injury or without causing any sort of discomfort, the robot will act as a physical therapy for the patients in the hospital. That is one of the practical example which we can consider. And the future directions which we can come across is research. We can do a lot of research on the robot joint manipulators, or we can have a better prediction and response to the environmental challenges, and we can go across the machine learning algorithm, incorporating machine learning algorithm or the varying conditions, like autonomously adjust to the various conditions. So we can come across these future challenges when we are considering for the advanced robotics, right? That is, we can do a lot of research in the sector of joints of the manipulator, or we can start working on the advanced version of giving the programming to the robot in terms of machine learning or artificial intelligence or neural networking, or we can also have the challenges based on various environmental conditions. So these are the future directions which we can come across, right? So these are the references which we have gone through for this particular content. So in today's topic, we have discussed about the various control strategies, we have seen the various applications, we have come across the key concepts, and we have known what the exact joint impedance regulation in robotics is about, right? Hope you have understood this concept, and in the next session, we will be dealing with another topic, right? So signing off for today, Dr. G. Hima Bindu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.